Hmm. Greetings, class. Welcome to Physics 390, class number 2. And this class is on momentum and the uncertainty principle. It's drawn from chapters 1.5 to 1.6 of your textbook. We're going to learn about how to look at expectation values conceptually, how to extract momentum from the wave function. We'll learn about a trade-off between the position and wavelength of a wave disturbance and how that impacts the uncertainty principle, which is a fundamental principle of quantum mechanics. So without further ado, we'll get started. So how do we interpret expectation values conceptually? So recall from the first lecture that the position expectation value is the expectation value of x is the integral of x times the probability density, where the probability density is the wave function squared. So when we multiply the probability density times dx, we get the probability for that small interval dx. We weight that with the particular x value and then add those all up, and that gives us the position expectation value. So, however, how do we interpret this conceptually? The expectation value is not the average of what you would get if you repeatedly measure the position for a single particle initially in the state psi. So for example, here is a state psi, or actually psi squared, showing a distribution of positions. And if you measured the position of that, it would, the first measurement would collapse the wave function to a given position. And for example, I've chosen the position C here, even though it's a little bit less likely, it certainly could be chosen. And further measurements on wave functions, further measurements on this particle would be with reference to this collapsed wave function. Now the collapsed wave function, after it collapsed, would spread just a little bit, but in general, all the further measurements would be very close to that initial position. So the first measurement you would get would be a representation of the distribution of psi, but after that, it would be just right around that first random measurement of psi that you got would be averaged in. So it wouldn't represent the full distribution of psi when you took the repeated position measurements on a single particle initially in the state psi. So what is the most helpful way to think about these expectation values conceptually? Well, we can think about them as the average of the positions measured for a set of particles all prepared in the same state psi. So for example, here is that same state psi, or psi squared, and there's many copies of it. So we have many particles all prepared in that same state psi, and this dot, dot, dot indicates there's more of them. And we measured all the particles from that same initial state psi, and then we average up all the values that we get, and that should be the expectation value x, or bracket x. Sometimes we call this, or often we call this set of particles an ensemble of identically prepared particles all in the same state psi. Okay, so that's just an interpretation of the expectation value as what you get when you take an ensemble of particles all in the state psi and measure the average position of that entire ensemble. That's what the expectation value represents, not repeated measurements on a single particle initially in the same state psi. Okay, so moving on, we can talk about the expectation value of momentum and the concept of an operator. So given our definition for the expectation value, as the integral from minus infinity to infinity of x times the probability density, we can differentiate this expression, and we find dx dt, the expectation value of x dt, is equal to, so we can take this d dt inside the integral. It doesn't affect the x variable because x doesn't depend on t here, it's just a variable. But it does affect the psi because psi depends on time. So one thing to notice here is that for the expectation value of x, we have a whole derivative d dt. And the reason for that is that if you look at the expectation value, it's integrated with respect to x, so it only depends on t. So we can just write d dt. Whereas once we bring that d dt inside the integral here, and we integrate on, or we differentiate with respect to psi squared is depends on t and x. So therefore we have to write the partial with respect to t of psi squared, because there's two variables there, x and t. Okay, so we have this expression here, and in our textbook, there's a number of steps which we follow to simplify this expression, or to put it in a different, more useful form. And using the Schrödinger equation and integration by parts several times, we can take this expression d expectation value of x dt and put it in this form, which is minus IH bar. You can recognize the IH bar is coming from the Schrödinger equation, over m times the integral of psi star d psi dx, where psi star is the complex conjugate of the wave function psi. Okay, so you can refer to the textbook for this derivation. I don't want to get too involved with that here. So note that what we get here is the so-called velocity of the expectation value. It's d dt of the expectation value x of x. It's not the velocity of the particle itself. Since we know, because of psi squared being the probability density of the particle, there's an indeterminacy in position. And so the particle does not have a single well-defined velocity, because it's kind of spread out in a cloud, and it can be at, when we measure it, at any given point. So it doesn't make sense to talk about a well-defined velocity, but we can talk about how the expectation value of x changes in time. So that would be the velocity of the expectation value, not an instantaneous velocity. So that's how to interpret dx dt here, expectation value of x dt. Well, we're usually interested in the momentum, p equals mv. And notice that this is the non-relativistic momentum. You remember from modern physics that in the momentum is mv gamma, where gamma is related to the speed of light. But if the velocity is low with respect to small with respect to the speed of light, gamma is essentially 1, and it just becomes p equals mv. So we won't be using any relativistic expressions in this course. Okay, so we can find the momentum would be mv, where v is the velocity of the expectation value. So that would be m d x dt, d expectation value of x dt. And that's just going to cancel this m up here. So we have minus IH bar integral of psi star d psi dx dx. Or more suggestively and more conveniently, we can write this as the expectation value of p is psi star. If we bring this minus IH bar inside and have the d over dx inside this bracket acting on this psi to the right, we can write it as the integral of psi star, and then this bracket minus IH bar d over dx, or partial with respect to x, of psi, okay? So the object in brackets, this minus IH bar d over dx, is called an operator. It's not a function because the derivative operation is not a function. This is an operator which performs some operation on whatever is to the right of it, okay? So this prescription is to take minus IH bar and then take the derivative with respect to x of what's to the right, but that would be psi here. So that's an operator. In this case, it's the momentum operator, because when we do it and then do that operator on psi and then integrate psi star times the result, we get the expectation value of momentum. So this object in brackets is called an operator, in this case the momentum operator, and it gets sandwiched between psi star and psi, and the whole sandwich is then integrated, as we see here, to give the expectation value of the related quantity, which in this case is momentum, okay? Now there are other operators. For a general physical quantity, which we can call Q, that's a function of position and momentum, we have the expectation value of Q as a function of position and momentum will be the integral of this sandwich again, psi star times the operator associated with Q, which we get just by substituting in for each x in the function Q. We substitute in x because x is the operator associated with the position. And for each p in the operator Q, we substitute in minus IH bar ddx. So one example of this might be the kinetic energy, which would be p squared over 2m. That would be Q, x and p would be p squared over 2m. So we would take p squared over 2m, substitute in for both p squared, the square of minus IH bar ddx, and we would get minus h bar squared over 2m d squared dx squared. So that would be our operator for the kinetic energy. But we'll see more examples of this coming up in the future. I just want to give you the knowledge that we have operators for different physical quantities, position, momentum, kinetic energy, total energy, angular momentum, and other things. Okay? So that's the concept of an operator. It gets sandwiched between the wave function complex conjugate and the wave function itself to give the, when integrated, to give the expectation value of the related physical quantity. All right, so using this information on operators, let's take a first look at something called Ehrenfest's theorem, which helps to relate the quantum to the classical behavior. Tries to give us a first look at answering the question, if the universe is quantum mechanical, if you look around, why don't you see weird quantum behavior like blurry objects and so forth? Why do we see things classically? So from the expectation value definition, which we looked at last time, P, expectation is m dx dt. We can solve for dx dt, or d expectation x dt. It's just expectation value of P over m. So that is the expectation value of x here in quantum mechanics evolves according to an equation directly analogous to the classical mechanical evolution equation for x, which is just dx dt, which is the velocity, is the momentum over the mass. Since classically P equals mv, this is just the definition of the momentum in classical mechanics. So we see that the form of the equation for quantum mechanics in terms of expectation values, d expectation value of x dt is expectation value of p over m, is the same form as for classical, except here it's not expectation values, it's the actual physical quantity instantaneous quantities of position and momentum. Okay? All right, so we have dx dt. What about dp dt? Well, we'll actually calculate this later in the semester in a future class. It's a somewhat involved calculation, but here we're just going to look at the result. And the result is that dp dt is the expectation value of minus dv dx. Okay? Well, I'll give you a second to think about what partial v partial x, the negative sign, would be. So I'll give you a second to think about that. So you might remember that the derivative of the potential energy, V, with respect to x is related to, or is equal to, when you take the negative, equal to the force. The force is minus the derivative of the potential energy with respect to the position. So we can say that the expectation value of P in quantum mechanics evolves according to an equation here. Dp dt is equal to minus dv dx expectation, which is the expectation value of the force, similar to the classical mechanical equation dp dt is equal to F. That's Newton's second law. Dp dt is equal to F. Okay? But there's a little bit of a hitch here. The directly analogous equation would actually be not dp dt is equal to the expectation value of the function f of x and t. It would actually be the f of the evaluated at the expectation value of x, comma t. Okay? And the reason for that is that the main physical quantities are p and x. So if we want a classical, an equation which matches or is directly analogous to the classical mechanical equation, we would want just to replace the p with the expectation value of p and x with the expectation value of x. That's not quite the same as taking the expectation value of f of x and t. Because if we take the expectation value of x, we're averaging over all x using the probability density. That puts us at a particular x, and we just evaluate the force at that particular x. Whereas when we take the expectation value of f, we're allowing x to range over all values and looking at the average value of f weighted by the probability density. So these two are not quite the same thing. However, if an object is very localized in space, okay, then these two things turn out to be quite similar, okay? Because if an object is localized in space, then the expectation value of x is taking a sample over a very small range of x. So x ranges over a very small range since the object is very localized. And then since the object is very localized, it's only going to spend time in that small area. So the expectation value of f of x and t is just going to be over that small range x as well. Okay. So both of these accomplish the same thing. F evaluated at the very localized average x will be about the same as taking the average of f of x and t. Since the average of f of x and t only has weight near the position, the average value of x. Okay? So if that's the case, then we have, if these two are approximately equal, then we have dp dt, and the quantum version is f of x and t, expectation value of x and t, which matches up with the classical mechanical equation. And the two quantum mechanical evolution equations then, in this case where the object is very localized, are directly analogous to the classical mechanical evolution equations. These two being the pair for the position expectation value in the position, and this one being the pair for the evolution of the momentum and the expectation value momentum. And this connects quantum mechanics to classical mechanics for everyday objects, because everyday objects are very localized in space. Well, they may have spatial extent, but their center of mass is very localized. There's no intrinsic or very little intrinsic uncertainty in where their center of mass is. So the spread in X is very small. And so when we move from the microscopic realm, where the object can be not very localized, so this analogy wouldn't quite hold, to the macroscopic, where the object is very localized in space, this analogy holds, and the quantum mechanical expressions for the evolution of the expectation values of X and P just smoothly merge into the expectation to the equations for the classical variables X and P, where the quantum uncertainty just gradually disappears to zero. Okay, so this is we'll go over this Einstein's theorem later in the semester in a class, but this helps connect and hopefully explain a little bit why we don't see quantum mechanical effects in everyday objects. Okay. All right, so let's move along to position and wavelength, a trade-off for waves. So suppose we have a wave that has lots of oscillations between 10 and 50 feet. It has a well-defined wavelength, which is about 6 feet. If you look at it here from let's see, from trough to trough here is about 6 feet, 30 to 36 feet. But the position of the wave is not very well defined, okay? Where would you say the position of this wave is? Well, it's stretched all across this string here, or rope. So well-defined wavelength makes the position hard to pin down. On the other hand, if we have just this pulse in the rope, it's a very well-defined position, about 25 feet in this where it's currently situated, but it's an ill-defined wavelength of the wave, okay? Because there's no multiple wavelengths here to determine the wavelength of the wave. So when the position is well-defined, the wavelength is not so well-defined, or it's ill-defined. So just reiterating that, the more defined the position of the wave, the less defined the wavelength, and vice versa. The more defined the wavelength of the wave, the less defined the position. So there's a trade-off between a clear definition of the position and the wavelength. Okay? So there's a theorem in Fourier analysis that makes this trade-off between the definition of the wavelength and the definition of the position mathematically precise. Okay? We'll look at this later, but here we just want to note that this trade-off has implications actually for the spread of the position and the momentum for a wave function. And that's going to lead us into the uncertainty principle. Okay? So how does that work? Well, you might remember from modern physics, there's something called the de Broglie relation. Recall from modern physics, the de Broglie relation connects the wavelength associated with a material particle to the particle's momentum. And this was this really interesting idea by de Broglie that a material particle with a certain momentum has a wavelength associated with it. So there's a wave-particle duality that's being expressed here. But anyway, there's a connection between the momentum and the wavelength, okay, expressed by P is equal to h Planck's constant over lambda. So the wave function is a wave. So if the position is well defined for a wave function, then the wavelength is ill-defined by our argument before. But if the wavelength is ill-defined, then the momentum is also going to be ill-defined, okay? Because the wavelength is related directly to the momentum. So if the wavelength has a large amount of uncertainty to it, the momentum will also have a large amount of uncertainty to it. On the other hand, if the momentum is well-defined for a wave function, then through this relationship, the wavelength is also well-defined. That implies the position is ill-defined, because a well-defined wavelength means that we can't nail down the position, okay? So there's this trade-off between the position and the momentum. If the momentum is well-defined, the position is ill-defined. If the position is well-defined, the momentum is ill-defined. And this trade-off can be expressed by an inequality involving the spreads or standard deviations of the position and the momentum, okay? So we express this by saying that the product of the spreads, the standard deviation of the position times the standard deviation of the momentum, must be greater than or equal to a minimum value, which is related to Planck's constant, h bar over 2, or h over 4 pi. Okay, so if we decrease, if we get our position well defined, that would mean our spread in x is small. That would mean that our spread in p would have to be large to satisfy this inequality, to get this product big enough to satisfy this inequality. So well-defined position goes to less well-defined momentum. On the other hand, if we shrink if we specify the momentum well by shrinking sigma p, then sigma x will have to rise to compensate. So we have this fundamental trade-off between the position and momentum. And that's called the Heisenberg uncertainty principle. And we will prove it later this semester. It expresses a fundamental conceptual principle, which is that we can't know the position and momentum of a quantum particle to full precision for both. There's a trade-off. The better we know the position, the less well we know the momentum. The better we know the momentum, the less well we know the position. Okay, and we think this is a fundamental property of nature. Well, it is. All experiments have indicated that. Okay, so that's the Heisenberg uncertainty principle. All right, so let's talk about applying the uncertainty principle. Along with its conceptual importance, the uncertainty principle is very useful for making estimates. Let's see how that could work. So consider the hydrogen atom, pictured here. So there's a bunch of sort of loops here, but there's just one, it's just supposed to represent one electron, since the hydrogen atom just has one electron. It's a sphere about 10 to the minus 10 meters in diameter, about 1 angstrom. So this is about 1 angstrom. We can approximate it as a cube, just for, again, this is an estimate. So we approximate it as a cube with side length of 10 to the minus 10 meters. Then the spread, sigma x for the electron wave function, since the electron fills up the space around the hydrogen atom, will be about that length, 10 to the minus 10 meters, okay? And then, since we have sigma x, we can use our relationship sigma x, sigma p is greater than or equal to h bar over 2 to solve for the minimum value of sigma p, which would be h bar over 2 sigma x. So plugging in for h bar as this constant over 2 times the sigma x of 10 to the minus 10, we get a sigma p of 5.28 times 10 to the minus 25 kilogram meters per second. okay? So then how can we relate that to energy? Well, the typical momentum px of the electron will be about equal to the spread of the momentum. Sometimes it's a little smaller than the spread value, sometimes larger, but the typical magnitude of the momentum will be about equal to the sigma p. And there's a relationship between the kinetic energy of the electron and kinetic energy of a particle and its momentum, which is that the momentum is, the energy, kinetic energy is p squared over 2m. So we would have k, the kinetic energy is px squared over 2m plus py squared over 2m plus pz squared over 2m, because it can have momentum in all the three directions. But all the three directions are about equivalent, so, or are spatially equivalent. So this is the same as just taking 3 times the momentum squared over 2m. So that gives 3 times our value for sigma p, since that's p, our typical value for px. Divide by 2 times the mass of the electron, and we get 4.59 times 10 to the minus 19 joules, or 2.87 electron volts, using the conversion. So how does that do? Well, the actual value of the kinetic energy of the electron in the ground state of hydrogen is 13.6 EVs. So the uncertainty principle here is accurate to within a factor of about 5, which is not bad. So it gives us a pretty good estimate of how much kinetic energy the electron would have. And notice that if we, we took the minimum spread in wavelength here. If we took double the minimum, this quantity here would be double. And then when we square it, it would be quadrupled. So this would be quadrupled. It would be about 11 or 12, which would be very close here. So the estimate is actually quite good. Okay, so what have we learned here? We have learned that how to interpret the expectation value in terms of an ensemble of particles being measured in the same prepared state. We've talked about the operator and the momentum operator. We've talked about Ehrenfest's theorem and the correspondence between quantum mechanics and classical mechanics as we get to macroscopic objects. We've talked about the trade-off between position and wavelength and the resulting trade-off between position and momentum, leading to the uncertainty principle, talking about the limits of our ability to know position and momentum at the same time to high precision. And then finally, we've seen an application of the uncertainty principle. Okay, so hope that's interesting and illuminating. And next time we'll talk about the time-independent Schrodinger equation. We'll take the Schrodinger equation and break it up into a break off the time dependence from the space dependence, look at the space dependent part, which is the time independent Schrodinger equation, and then apply it to the infinite square well, which should hopefully be somewhat familiar from modern physics. Okay, thank you for your attention, and I will see you in class.